If you ever felt like we're not doing enough examples, then this is your section. We already have 6 examples and there is still more to come. Here's number 7. And example 7 is about polynomial interpolation. So let's take x equal to the set of continuous functions on maybe the unit interval from 0 to 1. And let Gn denote a so-called grid of points x0, x1, and so on until xn, somewhere in this interval from 0 to 1. And let's assume the enumeration is so that the points are monotonically increasing. Note that this grid doesn't need to be equispaced, so the spacing between 2 points could be different from one to another. Of course, it makes things easier to make them equispaced, but not always better. Now take a continuous function f from our space x and look at the function values of f at our grid points. And now, because we call it polynomial interpolation, we are looking for a polynomial, let's say little p, of degree at most n, which is the same n that is enumerating our grid, so that p passes through these same green points as f does. So let's write down this task again. Find a polynomial p in Pn such that p of x equals f of x, but not at all points of the interval, only at the grid points. Well, because we have n plus 1 grid points, this here corresponds to n plus 1 equations. But on the other hand, the polynomial of degree at most n has n plus 1 parameters, so we have also n plus 1 degrees of freedom here. Okay, in every basic numerics course you learn that therefore there exists exactly one unique polynomial p which does the job, and this is the so-called Lagrange interpolation polynomial. And the word interpolation means that, well, you're just given the values at these finitely many green points, so you're given these green values, and you somehow have to invent something meaningful that's going on between them. And in this case, meaningful means polynomial of that given degree. Okay, so because this solution is unique, we can define a map that takes the green function f and produces the black polynomial p, and that's our projection Pn. Now not curly p, but straight p, Pn. So this function Pn here takes a continuous function f and produces a polynomial of degree at most n. But of course the set of these polynomials is again part of the continuous functions. So we end up in a subset of x, and that curly Pn is then the image of projection Pn, which is what we call capital Xn usually. So is it indeed a projection? Yeah, I think it is. So you just have to imagine that after applying Pn once, you're going to apply it again. So here you get a polynomial of degree at most n, which is assuming the same values at these grid points like p is. But p is already a polynomial of degree at most n, and apparently the solution is unique, so the result in the end must be p again. So indeed we see that applying Pn twice gives you the same as applying Pn once. So we can tick this box here. In case you're still wondering why there exists a unique solution, well, maybe either you look back to your numerics 1 course, Or maybe you want to understand this right now and here. Well, if you want to find such a polynomial, then of course you set up a polynomial with these n+1 degrees of freedom. And in order to find them, you have to solve a linear problem. And the matrix in this linear problem is a so-called Van de Monde matrix, containing the grid points here and powers of them. And for Van de Monde matrix, well, one can prove that it is invertible as soon as none of these grid points coincide. And this is what we are assuming here. We are saying they're all different from each other, and that gives you unique solvability of this linear problem. Okay, let me just state this word Van de Monde matrix here. The question that is a lot less obvious or simple is whether or not Pn converges to the identity, and if yes, then in what sense. One can show that this holds if you should not use the infinity norm. This is not going to work. Maybe you remember your numerics course explaining that when you blow up the degree of freedom, so you blow up your n, then of course you might throw 100 points inside your interval, but then you're looking for a polynomial of degree 100, and that's going to oscillate quite a lot. So most of the time it's far away from your black function, which means the infinity norm is not going to go to 0. It's probably just remaining large or maybe even growing. But what you can show is that you get convergence in the p norm with p less than infinity. Let me say in the 2 norm, if you choose your grid points wisely. And wisely in that case means you try something like zeros of Chebyshev polynomials. But let's not go much deeper here, because probably like in your numerics course, we're going to come up with a better idea now anyway. And that is example 8, spline interpolation. So again, start with, let's say, continuous function f on the interval 0, 1. And again, define a finite grid on this interval 0, 1, where now you're pretty safe if you take something equidistant, equispaced, you could say. But again, it doesn't have to be equispaced. But here it's a good idea to put x0 to be the left endpoint, which is 0 in our example, and xn the right endpoint. Okay, and then let's look at the graph of our function f and the values of f at the grid points. And now the difference between polynomial interpolation from example 7 and spline interpolation from example 8 is that you're no longer trying to find one polynomial that can deal with all these intermediate points, but instead you're looking for separate polynomials for every little subinterval here. And of course that makes life a lot easier, and you can formulate extra wishes. So as long as the only thing you want is to match these n+1 conditions here, these function values, then the most natural thing to do is just to take polynomials of degree 1 here. So you would just find a fine linear function for each of these subintervals, and thereby connecting the green points by just polygonal line. Of course, that's not great if you don't like these edges that you get here. So if you prefer something a bit smoother, then you could go up with your degree to polynomials of degree 2 or 3, and even formulate more wishes, like they should pass through these points and have the same derivative where they meet, which would of course give you a much smoother transition from one polynomial to the next, or from one subinterval to the next. So let me denote the polynomial on the first subinterval by P1, polynomial on the second subinterval by P2, and the polynomial on the last subinterval by Pn. Then in the end, the function that consists of all these polynomials, one glued to the next, could be S, and this is what we call a spline. So a spline is just polynomials, one glued after the other. And the typical conditions that you formulate would be the polynomial P1 has at the two endpoints of its subinterval x0 to x1 same values as the function f has, right? So you have point x0 the same as function f, and at point x1 the same as function f. Okay, in the same style you would the same two kind of conditions for the polynomial P2, now of course for the points x1 and x2, which is written down here. Okay, up until you reach the last polynomial Pn, and the endpoints there are xn minus 1 and xn. Okay, like I said before, you can make all of these here happen with linear or affine linear polynomials. So each one of these is just of the form something times x plus something. But if you want to get something a bit smoother here, then you could add further conditions like compatibility of the first derivative at these points where you glue one polynomial to the other. So you give your polynomials P1, P2 and so on a somewhat higher degree, degree 2 or 3. And in addition, you assume that the first derivative of P1 and P2 coincide at the point where they meet, and therefore they have the same steepness here, and you get something that's a lot smoother, of course. Okay, in the same style you would assume equality of first derivatives of P2 and P3 at matching point x2 and so on. And if you want, you can even copy the same line for second derivatives and so on. Okay, so we should formulate the task. So the task is to find polynomials P1 up to Pn, and depending on the degree that you allow here, you can formulate more or less of these wishes. So if I call that degree here k, then for k equals 1 you can formulate these. For k equals 2 you can go up to here. For k equals 3 you get so-called cubic splines, you can even go up to here. Okay, but the key point is that this k here doesn't blow up when you increase n. So you might want to make your grid denser, increase the number n, but you do not increase the degree of your polynomials, thereby avoiding the problem of oscillating that we have experienced in the previous example, number 7. Okay, maybe we should give this set of conditions here a name to, how about data consistency with f? So you want to assume the same data as your function f does. Okay, and then in the end you get your so-called spline s, which is not a polynomial itself, it's a piecewise polynomial function, right? So it's this polynomial on the first subinterval, and then that's polynomial on the second, and so on. Okay, and if you put your conditions right, and if they match the degree here, then again on each of these subintervals you get a unique solution, and therefore your spline S is uniquely determined, and you can again define a map taking your function f into this spline function S. Okay, and the n down here is essentially the size of your grid, right? -1. Okay, if you increase n, your grid gets finer, and this time indeed your approximation gets better, even uniformly. So you get not only that Pn is a projection, which is, well, you see this just like before. If you apply it again, you still stick with S. Okay, but this time it's easier to see that Pn converges strongly to the identity, even if you equip your space of continuous functions with the infinity norm, so uniform convergence. And this time you don't need the grid points to be like the zeros of certain polynomials, like in the previous example. All you need is that the spacing between your grid points should not become too irregular. So if you compare the largest gap and the smallest gap in your grid, then that quotient should not blow up. It should not go to infinity, or yeah, it should be bounded somehow. And if that happens, then you're guaranteed convergence even uniformly here. Okay, and last but not least, let's try spline interpolation on an unbounded interval. So this is example 9. So in the previous examples, our interval was always bounded. So for simplicity, we always took the interval from 0 to 1. Of course, we could have taken the interval from 0 to 10 or from 1 to 11 or something. But the new quality here is that we are looking at an unbounded interval. And then the idea is to use 8, but with a sequence of grids where each grid is getting denser as n increases, but at the same time the interval is growing. Okay, so let me make one suggestion here. Let me take the grid Gn of these points. So the points are k divided by n, where k is running from 0 to n. So you will get equal spacing starting from 0. Spacing is equal to 1 over n. And the last point will be when k equals n. So this is n divided by n is at 1. Now you say, hang on, this is just giving you a good grid for the previous example where you want to sample your interval from 0 to 1, finer and finer, which is of course what you're doing here. So the new idea is to not end at n, but carry on until n squared. So your last point will not be 1, it's going to be n. But still the spacing is 1 over n. So your grid is getting denser and longer at the same time when n is growing. Okay, now I think after 9 examples, everyone's happy example-wise.